14 billion miles from Earth, farther than any human-made object has ever traveled, a spacecraft launched back in 1977 is still awake, still listening, and it has been picking up something strange. Not a voice, not a signal in the science fiction sense, but a real, measurable frequency, a faint, steady hum coming from the space between the stars itself. And scientists confirmed it is not noise, not a glitch, not equipment failure. It is the actual sound of interstellar space. Stick around, because by the end of this video you're going to understand exactly what Voyager 1 detected, why it took scientists years to be sure it was real, and why this quiet little signal is quietly rewriting what we thought we knew about the space beyond our solar system. And if you want more real verified space stories like this one, go ahead and hit that follow button now, because we are just getting started. Let's back up first and talk about what Voyager 1 actually is, because the spacecraft itself is honestly just as remarkable as anything it has discovered. Voyager 1 launched from Earth in September of 1977, built with technology that would look almost primitive by today's standards. It has less computer memory than a basic calculator you would find in a desk drawer, and it originally sent data back to Earth using about the same amount of power as a couple of household light bulbs. Its original mission was to fly past Jupiter and Saturn, take detailed photographs, and study those planets and their moons up close. It did exactly that, and it did it so well that NASA extended its mission far beyond anything originally planned. Instead of shutting down once its planetary flybys were finished, Voyager 1 kept going and going and going. It kept climbing outward, further than Jupiter, further than Saturn, further than the outer edges of what most people think of as our solar system. In August of 2012, after 35 years of travel, Voyager 1 crossed a boundary called the Heliopause. Think of the Heliopause as the edge of a giant bubble blown outward by our sun. Inside that bubble, the solar wind, a constant stream of charged particles flowing off the sun, pushes outward and dominates the environment. Once you cross the heliopause, the sun's influence weakens to the point where the pressure of the wider galaxy, the interstellar medium, takes over instead. Crossing that boundary meant Voyager 1 had officially left the solar system's bubble behind and entered interstellar space, becoming the first human-made object in history to do so. That alone would already make Voyager 1 one of the most significant objects humanity has ever built. But leaving the bubble was not the end of the story. It was actually the beginning of a whole new chapter, because once Voyager 1 was out there, floating in the true space between the stars, its instruments started picking up something nobody had ever measured directly before. Here is where we need to talk about what that frequency actually is, because it is genuinely one of the more elegant discoveries in modern space science, and it has nothing to do with anything artificial or intentional. Voyager 1 carries an instrument called the plasma wave subsystem. In simple terms, this instrument is built to detect vibrations and oscillations in plasma, which is basically ionized gas that has had electrons stripped away from its atoms, leaving behind a charged, electrically active soup of particles. Plasma is actually one of the most common states of matter in the universe. Stars are made of it. The solar wind is made of it. And the thin, nearly empty space between stars is also filled with a very sparse, very faint version of it. At first, Voyager 1's plasma instrument only detected sudden, dramatic bursts of activity. These happened when powerful eruptions from our own sun, called coronal mass ejections, sent shockwaves rippling outward through the solar system and beyond, eventually slamming into the interstellar plasma surrounding Voyager 1 and shaking it violently enough to register clearly on the spacecraft's instruments. Scientists detected a few of these shockwave events in the years right after Voyager 1 crossed into interstellar space, and each one gave researchers a brief, valuable snapshot of the density of the plasma out there. But these events were rare, unpredictable, and temporary. In between them, Voyager 1's readings mostly went quiet, and researchers had no reliable way to keep measuring the interstellar environment during those long gaps. That is exactly the problem a team of researchers led by Cornell University set out to solve. Instead of waiting for the next rare solar shock wave to light things up, they went back through years of quieter data from Voyager 1's plasma instrument, the kind of data that had mostly been considered background noise, and they looked closely for anything faint but consistent hiding underneath. What they found surprised almost everyone involved. Buried in that supposedly quiet data was a persistent, continuous signal, a narrow, steady frequency that never really turned off. It was not a burst. It was not tied to any single dramatic event. It was just there, quietly humming along, week after week, month after month for years. This is the discovery that eventually got the nickname the interstellar hum, and it turned out to be one of the clearest continuous measurements of interstellar plasma density ever recorded. The frequency itself sits in a narrow band, hovering around 3 kilohertz, which is technically within the range of pitches the human ear can hear, although this is not sound traveling through air the way a hum from a speaker would be. There is no air in interstellar space to carry sound the way we normally think of it. What Voyager 1 detected is an electromagnetic oscillation in the plasma itself, which scientists then translated into an audio frequency so people could actually get a sense of what it represents. Researchers described the tone as faint and monotone, a low, steady drone with almost no variation, precisely because it comes from such a narrow band of frequency rather than a rich mix of different tones. Now here's the part that makes this discovery genuinely valuable rather than just a neat curiosity. That frequency is not just an interesting sound, it is a direct measurement tool. The specific frequency of a plasma oscillation is tied mathematically to the density of the plasma producing it. Denser plasma vibrates at a higher frequency. Thinner, more spread out plasma vibrates at a lower frequency. By carefully tracking small shifts in that steady hum over time, researchers can actually calculate how the density of the interstellar medium changes as Voyager 1 continues drifting further and further from our Sun. In other words, this quiet, continuous frequency works almost like a slow, ongoing readout of the density of the space between the stars, updating itself in real time as the spacecraft moves through different regions. That is an extraordinary capability because before this discovery, scientists could really only get density readings from those rare, violent shockwave events triggered by solar eruptions, snapshots separated by long gaps of total silence. The persistent hum changed that completely. It gave researchers a continuous, ongoing stream of density data instead of occasional flashes, letting them build a much smoother, much more detailed picture of what interstellar space actually looks like just beyond our solar system's edge. To understand just how big a shift that is, think about the difference between checking the weather outside once every few years during a passing storm versus having a sensor that quietly reports conditions every single day without fail. The shockwave events gave researchers something like the storm readings, useful but rare and disconnected from each other. The persistent hum works more like that daily sensor, a slow, steady drumbeat of information that lets scientists watch trends unfold instead of guessing what happened in the long, silent gaps between events. For a spacecraft this far from home, sending data back at painfully slow rates, having any kind of continuous signal to lean on, is a genuine gift for researchers trying to build an accurate long-term picture of the region. Researchers found that this persistent oscillation had actually been present in the data for years before anyone fully recognized what it was. Once they understood what they were looking at, they could trace the signal back and see that it had been quietly running in the background of Voyager 1's readings since not long after the spacecraft first crossed into interstellar space. The findings were formally published in the scientific journal Nature Astronomy, led by Cornell astronomer Stella Koch-Ocker, alongside a team of researchers who spent painstaking hours combing through faint, noisy data collected from more than 14 billion miles away. It is worth pausing here to really appreciate just how difficult that kind of work is. Voyager 1 is so far away that even traveling at the speed of light, a radio signal takes over 20 hours just to reach Earth from the spacecraft's current position. The data itself trickles back at an incredibly slow rate compared to modern technology, largely because Voyager 1 is still relying on communication systems designed in the 1970s. Digging a faint, steady signal out of years of noisy, slowly transmitted data and proving that it was real and not some artifact of the equipment or the transmission process took careful, patient scientific work. This was not a dramatic, instant discovery. It was the result of researchers quietly sifting through mountains of old data until a consistent pattern emerged. So what does this hum actually tell scientists about the wider environment Voyager 1 is now traveling through? For one, it confirms that interstellar space, while incredibly sparse compared to anything inside our solar system, is not perfectly empty. There's a thin, continuous presence of ionized gas out there, quietly vibrating, quietly present, filling the vast gaps between star systems. Scientists have long known theoretically that the interstellar medium contains gas and plasma, but having a direct, ongoing physical measurement of it, coming straight from an instrument actually sitting inside that environment, is a completely different level of confirmation. It also gives researchers a genuine tool for tracking how that environment changes as Voyager 1 continues its journey outward. As the spacecraft drifts further from the heliopause and deeper into true interstellar space, the density and behavior of the surrounding plasma is expected to shift gradually. By tracking small changes in the frequency of that steady hum over months and years, scientists can begin mapping out how the structure of the interstellar medium varies with distance, giving them a kind of long-range, slow-motion survey of a region of space that no other instrument has ever been able to study this directly. There is also a bigger picture piece to this. Our sun's heliosphere, the enormous bubble carved out by the solar wind that surrounds our entire solar system, does not sit in a perfectly stable, unchanging patch of the galaxy. It moves through the interstellar medium as our solar system travels along its orbit around the center of the galaxy. And the shape and behavior of that bubble is influenced by the pressure and density of the interstellar material pressing in from outside. Understanding exactly how dense, how active, and how variable that surrounding plasma really is helps scientists build a much more accurate model of how our heliosphere is shaped, how it protects the solar system from harmful cosmic radiation, and how it might behave differently as our solar system continues moving through different regions of the galaxy over extremely long timescales. Now, because headlines love a dramatic hook, and because the phrase interstellar frequency naturally invites some wild speculation, it is worth being very clear about what this discovery is not. This is not an artificial signal. This is not a transmission, a message, or anything resembling communication. Researchers were not searching for extraterrestrial technology when they found this, and nothing about the signal behaves the way an intentional transmission would. It behaves exactly the way a natural plasma oscillation is expected to behave, a steady, narrow band hum produced by the physical properties of ionized gas reacting to background energy in its environment, specifically low energy, cosmic rays gently stirring the plasma and keeping it subtly vibrating over time. Scientists involved in the research were direct about this. That distinction matters, because the real discovery here is arguably more impressive than any imagined alternative. Humanity built a machine using technology from the 1970s, sent it further than anything else we have ever created, and that machine is still functioning well enough, still sensitive enough to detect and transmit back a signal representing the physical texture of interstellar space itself. That is not science fiction. That is real, ongoing, verified science, still unfolding today. It is also worth putting this discovery in context alongside everything else Voyager 1 has already accomplished, because this spacecraft has been rewriting expectations for decades. It was never originally designed to operate this long or travel this far. Its planetary flyby mission at Jupiter and Saturn was considered a complete success on its own, and anything beyond that was essentially bonus territory. During its flyby of Jupiter, Voyager 1 delivered some of the first close-up evidence of active volcanoes on the moon Io, a discovery nobody fully expected going into the mission. At Saturn, it captured detailed images of the planet's rings and its moon. There's also a reshaped how scientists understood that entire system. Those early wins alone would have made the mission a resounding success, beyond even if the spacecraft had gone silent shortly afterward. Yet here it is, well over 4 decades after launch, still sending back usable scientific data from a region of space nothing else built by humans has ever reached. Its twin spacecraft, Voyager 2, launched around the same time and eventually crossed into interstellar space of its own in 2018, giving scientists a second vantage point to compare readings from a different direction, adding even more depth to what researchers can learn about the shape and behavior of the interstellar medium surrounding our solar system. Both spacecraft are, of course, aging. Their power sources rely on the slow, steady decay of radioactive material, which means their available power shrinks a little more every year. NASA engineers have had to make careful, deliberate choices about which instruments to keep running and which ones to power down in order to stretch the spacecraft's remaining working life as long as possible. In recent years, mission controllers have had to shut down individual science instruments one at a time, prioritizing whichever tools give the most valuable ongoing data per watt of remaining power, a genuinely difficult balancing act for a machine that cannot be repaired, upgraded, or even physically inspected ever again. Every additional year of data these two aging explorers manage to send back is treated as an incredibly valuable, essentially irreplaceable resource, because building and launching a genuine replacement, one that could travel this far and operate this long, would take decades, even with modern technology. It is worth comparing this to other missions studying the same general region from different angles, because Voyager 1 and Voyager 2 are not the only tools scientists have for understanding the edge of our solar system. A smaller NASA mission called IBEX, short for the Interstellar Boundary Explorer, orbits Earth and studies the heliosphere from a distance, mapping the boundary indirectly by detecting particles bouncing back from that region. It offers a wide global view of the heliosphere's shape, without ever leaving the vicinity of Earth. Voyager 1 and Voyager 2, on the other hand, offer something IBEX simply cannot: direct, on the ground, or rather on the spacecraft, physical measurements taken from inside interstellar space itself. Combining the wide-angle view from missions like IBEX with the direct close-up readings from the Voyager probes gives researchers a far more complete picture than either approach could provide on its own. Scientists have also floated concepts for a dedicated future interstellar probe, a purpose-built spacecraft designed from the ground up to study this region with modern instruments. But any mission like that is still in the early planning stages, and would take many years to design, build, and launch, let alone travel far enough to matter. For now, and likely for a long while still to come, the aging Voyager spacecraft remain humanity's only direct source of information from actual interstellar space. That is part of why this discovery matters so much to scientists. It is not just a neat one-time finding. It represents an ongoing capability, a real continuous stream of data about a region of space that would otherwise remain almost completely unmeasured. coming from instruments that cannot easily be repeated or replaced anytime soon. Every additional month, Voyager 1 keeps functioning out there, adds more to a data set that quite literally cannot be gathered any other way with our current technology. It is also worth noting how differently this quiet, methodical discovery unfolded compared to the way a lot of headline space stories usually break. There was no dramatic countdown, no live broadcast, no single flashy image released to the public in an instant. This was years of patient data review, careful statistical checks to rule out equipment glitches or transmission errors, and a peer-reviewed publication process before anyone confirmed anything publicly. That slower, more careful pace is exactly how legitimate science tends to work, even when the end result turns out to be something as evocative as a genuine ongoing sound from interstellar space. It rarely looks like the movies. It looks like patient people quietly checking their work. There's a broader scientific mission wrapped around all of this too. Understanding the structure of the interstellar medium is not just an abstract curiosity. It directly connects to how scientists understand cosmic rays, high-energy particles that stream through this galaxy and can pose risks to both spacecraft electronics and, over long enough exposure, biological tissue. It connects to how researchers model the protective boundary our heliosphere provides against those cosmic rays. And it connects to broader questions about how stars, including our own, interact with the wider galactic environment as they travel through it over enormous timescales. A steady, ongoing measurement of plasma density just outside our solar system's boundary feeds directly into all of these bigger scientific pictures. It also connects to something a little more personal for a lot of people who find this kind of story fascinating. Voyager 1 was never meant to still be talking to us after all these years. It carries a golden record on board, a literal physical time capsule containing sounds, images, and greetings meant to represent humanity to whatever might eventually encounter it, drifting silently through the galaxy long after the spacecraft itself stops functioning. Knowing that this same aging explorer, carrying that message meant for someone else entirely, is still actively feeding us real scientific data about the true nature of interstellar space gives the whole story an extra layer of meaning. It is simultaneously humanity's furthest reaching physical object and one of our most reliable ongoing instruments for understanding a part of the universe we have never been able to study directly any other way. So what happens from here? Scientists continue monitoring Voyager 1's plasma wave data, tracking small shifts in that steady frequency as the spacecraft keeps moving further from the heliopause. Every subtle change adds another data point to researchers' understanding of how interstellar plasma density varies with distance, information that simply cannot be gathered through any telescope, no matter how powerful, because telescopes observe from a distance while Voyager 1 is physically there, sitting inside the environment it is measuring. Researchers are also using this data alongside information from other missions studying the outer boundary of our solar system, building an increasingly detailed combined picture of exactly how our heliosphere interacts with the surrounding galaxy. Every additional piece of information helps refine models of how much protection our solar system's bubble actually provides against the wider galactic environment, and how that protection might shift over the extremely long timescales our solar system continues drifting through different regions of the Milky Way. There's also a practical, forward-looking reason. This kind of long-term monitoring matters beyond pure curiosity. As human spaceflight ambitions continue expanding, understanding cosmic ray exposure and the structure of the radiation environment beyond our immediate solar neighborhood becomes more than an academic question. While no crewed mission is anywhere close to reaching interstellar space any time in the foreseeable future, the fundamental physics Voyager 1 is helping researchers understand today how plasma behaves, how cosmic rays interact with it, and how our heliosphere's protective bubble actually holds up against the pressure of the wider galaxy, feeds directly into long-term planning for deep space exploration technology and radiation shielding research decades down the road. Before we get to the bigger picture, if you have made it this far and you are genuinely enjoying learning how a 50-year-old machine is still teaching us new physics, take a second and hit that follow button now. Because this channel exists to keep bringing you stories exactly like this one, grounded in real published research instead of vague online speculation. There's also a quieter, more reflective piece to this story, worth sitting with for a moment. When Voyager 1 launched in 1977, nobody involved in the project could have guaranteed it would still be operational decades later, let alone still capable of detecting subtle physical phenomena in a region of space it was never specifically designed to study. Engineers built it as sturdily and as thoughtfully as the technology of the time allowed, but the sheer length of its ongoing usefulness has genuinely exceeded almost every original expectation. Every new discovery it continues to deliver, including this persistent interstellar hum, is really a testament to careful engineering from nearly 50 years ago, still paying scientific dividends today, far beyond anything its original designers could have confidently promised. It also helps to appreciate just how unusual it is for a discovery like this to come from data that had already been sitting in archives for years before anyone recognized its significance. This was not new data collected specifically to hunt for a hum. Researchers went back through readings that had already been transmitted to Earth, sitting quietly in scientific archives, and applied fresh analysis techniques to spot a pattern that had simply gone unnoticed the first time around. That is a reminder that a lot of major scientific discoveries do not come from brand new instruments or brand new missions. Sometimes they come from someone taking a second, more careful look at information we already had, asking a slightly different question of the same dataset, and finding something nobody had thought to look for the first time through. Think about the scale of that for a second. 14 billion miles away, in a region of space so thin and so empty that describing it as a near vacuum barely captures how sparse it really is, there is a small, aging spacecraft still faithfully doing its job, still quietly recording the texture of the space around it, and still managing to send that information back across an almost unimaginable distance to scientists here on Earth. That signal takes over 20 hours just to arrive. And once it does, researchers carefully piece together tiny fragments of data into a clearer and clearer picture of what the true space between the stars actually sounds like, physically speaking, for the first time in human history. To wrap this up simply, Voyager 1 crossed into true interstellar space back in 2012, becoming the first human-made object to ever do so. Once there, its plasma wave instrument began picking up occasional bursts of activity triggered by shock waves from solar eruptions, but researchers eventually discovered something even more significant, hiding quietly in the background data, a persistent, continuous frequency, a faint, steady hum produced by the natural vibration of interstellar plasma itself. That discovery, confirmed and published by a Cornell-led research team, gave scientists their first reliable ongoing method for measuring the density of the interstellar medium surrounding our solar system, instead of relying only on rare, unpredictable shockwave events. The signal is completely natural, tied directly to the physics of plasma reacting to cosmic rays, and it is helping researchers understand how our solar system's protective heliosphere interacts with the wider galaxy. It is not a message. It is not artificial. It is something arguably more remarkable. Real, ongoing physical evidence of what the actual space between the stars is like, gathered by a nearly 50-year-old spacecraft still quietly doing its job farther from home than anything else humanity has ever built. That is the real story, backed by real data, from a real spacecraft, gathered by real scientists, carefully working through faint signals sent back across 14 billion miles of empty space. If this gave you a new appreciation for what a decades-old machine can still teach us about the universe, follow this channel, because we're going to keep tracking every confirmed update on stories like this one as new data continues rolling in. Drop a comment telling me which part of this surprised you the most, and share this with someone who would find it as fascinating as you clearly do. We will see you in the next one.